unusual. I seem to have a combination of Texas jet lag and airplane flu that had me on my back the whole of yesterday, so I'll try and keep it together. Essentially, this is a talk about our use of Python in radio astronomy. So I work for SKA South Africa, which is building a telescope known as MeerKAT, which is a precursor to a larger thing called the SKA. So I'll go quite quickly through. Radio astrologer is what I'm called a lot. I don't know if this happens to optical astronomers. Maybe they're optical astrologers, but it's an interesting one to me. So optical astronomy, it's pretty, most people know what we're talking about when you talk about optical astronomy. Look up at the night sky, see what you can see with your eyes. It's pretty spectacular. You don't need a massive telescope to do a lot of cool things. A 2.2 meter telescope lets you get a pretty good view of Centaurus A. Obviously, that's only a small part of the picture. I'm preaching to the converted here, but we're never going to know what the sinister Google projects are up here in the gamma rays if we don't look outside of just the optical domain. So what radio astronomy is really interesting for is taking normal optical data. You use a big telescope like the JVLA in New Mexico, and you add radio imaging data to it, and you see something completely different that you didn't expect. When you look in the optical, you see a nice galaxy, as you expect from theory. What you miss out is these jets of gas that are roughly the same size as the galaxy itself. If you never looked in the radio, you wouldn't know it was there. If you go even further out, there's that same optical little piece in the middle. You can't really see this that well with the lights. But essentially, if you look at the radio emission from Centaurus A in its entirety, we're talking about 9 degrees on the sky. The full moon is half a degree up in the sky. So if we could see this thing with our eyes, apart from our eyes needing to be like a meter in diameter, it would be pretty spectacular covering the sky. So it's a whole world of information that multi-wavelength astronomy is all about. And my particular field is radio astronomy. What's interesting as well about radio astronomy, and you might have noticed, is that we combined a relatively small optical telescope, 2.2 meters, with currently the largest radio telescope in the world to get that image. The reason for that is just comparative energy. It takes about a joule to melt a snowflake. We're talking about less than a microjoule for the kinetic energy of a mosquito in flight. The JVLA in a day collects that much, 100th of a petajoule. So you're building a nice big telescope, but it's really not getting much information. It's not getting much energy from out there, so we need to build them bigger and bigger to do our science. And the first way we did that was through scale up. So you build bigger and bigger dishes. It's kind of a natural flow of things. Once you get to about a 100-meter class dish, the mechanical engineers will start getting a bit panicky, and the costs go through the roof, because to make a mobile structure that size gets quite crazy. So what you do is you scale out. And so here's one we built earlier. This is the Karoo Array telescope. This is in our backyard. I'm located in Cape Town, South Africa. This is in the Karoo Desert. It's about 900 kilometers away from our engineering office. And we've had these 7 antennas operating out in the field since 2009. That's a stepping stone to building bigger and better things. Currently, we're building what's known as MeerKAT. KAT stands for Karoo Array Telescope, and Meer is Afrikaans word for more, so it's just more of the same. This will be 64 antennas, again, located in the Karoo. And when this comes online in 2016, it'll be pretty much the most sensitive radio telescope in the world in its frequency band, which is L-band, so 1 to 2 gigahertz nominally. That's a stepping stone to yet another bigger thing called the SKA. So the SKA is this international collaboration to build the biggest radio telescope the world has ever seen. And there was a big competition between ourselves and the Australians to host it. In the end, it was kind of a Solomon's child cutting in half type thing. And 1/3 of it went to Australia, 2/3 of it going to South Africa. Essentially, by 2025, we'll have 3,000 odd 15-meter diameter antennas sitting out in the Karoo. Big telescope, mostly for us, means big data. So the SKA in 2025, we're looking at about an exabyte a day of data. That's not raw data, that's data we actually have to look at and take some cognizance of. So the problems to come for us are pretty challenging. At the moment, it's quite doable, but it's scaling up quite exponentially. Big data also means lots of big energy concerns. And one thing that people sometimes don't realize is energy for I/O. And particularly with a big telescope like this, which is distributed over long baselines, the I/O costs start to dominate quite substantially. And for the SKA at the moment, we're talking 16 megawatts just to move the bits around out in the field. Never mind doing anything else, we need to build a power station just to move our bits back to our central location. So how do we build these big, complicated beasts? Now, I'm almost on Python, I promise you. I won't keep yapping on about radio astronomy forever. So how do we build these things? Well, first of all, we need big iron. Not that kind of big iron, this kind of big iron. We need to build trenches and stuff, but it's very interesting. We need this kind of big iron, so we need a big compute facility. Again, there's nice, scary numbers at the bottom here, mostly to get funding, but this is pretty much what it's going to be. We're talking ExaFLOPs, exabytes, everything's exa this. So it means, the industry players flock to us and give us lots of money, which is nice, but it still means we have to deliver 3 or 4 ExaFLOPs into the desert by 2025 in cost, in power budget, which is going to be a problem. So big lines are very well, but big software is where I'm interested in. And so obviously, if we're going to use the most popular language on the planet, we're going to use COBOL, 200 billion lines of COBOL and keep growing. But obviously, for us, that's not much of a realistic solution. So I sort of look at the language question with 2 slides. The first slide is kind of the philosophy that we are currently using in MeerKAT. Most of this is obviously common sense. People have talked about this today in many forums. Delivering something today is better than tomorrow, particularly in these kind of scientific fields where it's more important to get some decent research out today than to come for some sort of perfection tomorrow. Scale requires better ideas, not more code. It's very easy to throw code at problems rather than kind of rethinking what you need to do. Simple is better than complex, a very obvious trotted out one all the time. But we still find lots of people like, I must have a complex, hard solution to problems rather than simple. Optimize last. In my opinion, a lot of language choice comes down to people optimizing first and assuming that things are going to be too hard to do and require too much performance. So they optimize ahead of time by picking a language. Commodity is king, so use what's available, use what's off the shelf, use the tools everyone else is writing for you. And perfection is an illusion is my favorite one. The people chasing that are going to chase it for a long time. Another thing is David Beasley made this great comment last year at Euro SciPy 2012. Life is too short to write C++. Obviously, there's some dissenters, but personally, for me, that's quite good. So you join those 2 slides together, and you end up with Python. Lots of Python, so we have 30-odd in-house modules and growing all the time. The usual dependencies, we use everything that's out there, which is fantastic. Everyone just provides it for free. We hopefully provide a bit of value back to some of these projects as well, which is good. And we use it in all the obvious places. So we use it for our full control system. So we've been using IPython since 2008 or so and augmenting it into an interactive shell, which lets us drive our whole facility. One of the key things here that's made it really good is we do all our connection and discovery on an introspection basis. So we never hard code what the telescope looks like. Anytime you create a control session, it figures out what's available to be used. And this is really good for developing and growing infrastructure, and it's been very good for us. Another thing we do a lot of is this concept of kind of live observing mixed in with things. And this has been a powerful tool for us to explore what the telescope is doing. It lets you, in an IPython session, get full access to what the telescope is doing, as well as data coming in a live fashion. And then you can bring your full suite of tools to bear on it as it arrives immediately. And this has been really great because it means you can just sit at home in the bed and collect your data and figure out what's broken with your telescope as you go. We spent quite a lot of time on visualization. Obviously, we use matplotlib a lot. We wrote this pretty outdated now MPL H5 Canvas backend, which has been superseded mostly by transparent PNG transmission as an animated web framework, which is probably a better idea. We wrote this a while ago, and it was quite cool when we wrote it, and we still use it quite a lot. So those are all obvious places. So the question we asked is, well, how far down can we go with Python before we hit the turtles and have to stop? And these are some slides that I sort of presented to my radio astronomy colleagues when I was trying to convince them not to use C++. And it's the usual sort of stuff. Everyone knows these sort of things. Some simple examples. Python is pretty slow. No, it's really, really, really terribly, horribly slow. You can never consider using it, etc. My response is always, you're just holding it wrong. And here's the trivial example why. Obviously, if you just have some serial code in Python, it's not going to be great. You can vectorize it and gain some good wins in that respect. So this slide was great because I had it prepared, waiting for an audience member to stand up and say, but no, it's just C underneath. And I was like, yes, I know it's C underneath, but I didn't have to write it, which is great. And I could just write a simple vectorization, and I gained all the benefits of all the people who can write better code than me. And I can just go to the beach, which is great. So we don't get paid by the K-lock either, so that's also nice. So okay, we're still slower than C, but fundamentally, I don't think language dictates performance particularly. I mean, it does to some extent, but not massively. In Python's case, we're mostly blaming CPython here, which is why you can see the benefits of things like Number and PyPy. So one of the questions we need to ask, though, is, okay, it's a little bit slower than C, but is that a problem? How fast do we need to be? So that's your CPU most of the time, especially if you're a radio astronomer. Your CPU is just sitting there doing nothing. It's completely bored with itself. It can't do anything. And the reason for that is a lot of our data processing is pretty mathematically sparse. Our number one problem is convolutional gridding, which we need to do a lot of. And basically, if you take a modern-ish CPU, we need 64 gigabytes a second to keep our CPU busy. And realistically, that's about an order of magnitude less than you've got. There's certain issues with caches and compression, et cetera, but you're in that kind of ballpark. There's no way you're saturating a single die on a modern PC with 64 gigabytes a second. So if our I/O is efficient, then we can sacrifice up to an order of magnitude in CPU performance, and our overall application doesn't suffer. Obviously, lots of disclaimers apply for these kind of outrageous statements. There's two ways we do I/O quite well, one of which is we use this protocol we invented, because everyone has to invent your own protocol, which we call SPEAD, because speed was taken and we couldn't Google it, so we SPEAD it. Essentially, what's nice about this is it's basically a NumPy array transport, but it works across a whole range of architectures. So, if we have an FPGA implementation, we have RDMA direct into GPUs, we have the normal Pythonic implementations, but all this way through here, we never do anything to the binary bit. We just change and strip headers, and it always looks like a NumPy array if you need it. And that means that we can get access to our data really fast. Our I/O is very efficient because basically, we zero copy it into user space, throw the pointer across to Python, and the data is there, as you guys know. The other thing we do is we use PyTables quite a lot, so BLOSK is really good. This graph just shows you that effectively you can get better than raw disk performance if you use HDF5 and you use BLOSK well, so PyTables works really well for us. So our I/O is pretty good as we go. Another thing that I like about Python is that, in my opinion, there's two basic ways to get performance out of an application. You can have better algorithms, or you can have better code. But those two things only help you if that barrier is low. For instance, there's a lot of packages in radio astronomy that are 20 years old and have 1 million lines of Fortran. And the barrier to entry of changing those, making them better, is just massive. You can't throw away that code. You can't change the algorithm because you can't understand it. No one can understand it. No one's left alive who understands that code. So for us, and a classic example of this is something we did very recently, I won't go into the detail, it's a very trivial algorithm, but basically one of our major challenges is solving this calibration problem where we have unknown gains on each instrument, and we have a lot of measured visibilities. And so if we've got many more measurements than unknown complex variables, we can just do a minimization, and the simple thing to do is Levenberg-Marquardt. If we do a simplistic thing, what we've done here is we've had a bad code implementation and a bad algorithm for the problem we're facing, and so it's slow. And so we looked, and people worked together, and we collaborated as a sort of community, and we came up with a better algorithm, which was very easy for us to implement because this was so little code that we could just throw it away and start implementing this new one. But we implemented it in a silly way, a scalar way that didn't work very well. But again, this was only like half an hour of code, so we threw that away and made a better one. And then it was much faster. And then we used Number, and it was even faster. But the beauty of this was that it never cost us much to do this. The barrier for switching at each time was so low that we could afford to do it. So this idea of having good ideas and being able to throw away stuff around it, I think, is very useful. And I find Python suffers a lot less from this kind of entrenchment philosophy that it's so big and so complicated, and we can't afford to change. And I think that's worked well for us. I think LLVM, we've been using this for quite a while. I'm very excited, particularly about where you go from bitcode. I think once you're in the IR form, the ability to go to things like PTX and CUDA, OpenCL, JavaScript. I mean, Scripting is just lovely to play with. I think this is kind of where the future is going, where we get to the point where you're kind of language agnostic upstream of the IR to some extent. The IR is nice and flexible. You can encode a lot of parallel ideas in it. So with the right kind of hinting, you can take any language and get it into decent IR. So we might as well use Python. And once we're in a decent IR, you can target all these backends dynamically at runtime. I think particularly for green scheduling, where you want to run the same code in different ways on different architectures at different times, this is really useful because you have one set of IR and you pick a whole lot of backends that you need as you go. So for us, our biggest cost is development time, not hardware, and this is where high-level languages win for us. In the Dutch Research Observatory, Astron recently developed a software correlator, and they spent 2/3 of their money on coding and only 1/3 on the hardware of the thing. And it's a good example of people actually cost a heck of a lot more than CPU time, and we've mentioned this many times, but it's so true. Finally, just to wrap up, community building is a big part of this. It's nice we give back as much as we can to open source. We've got a lot of stuff on GitHub. That's what Python's great for. I think that welcoming community, the sharing, those kind of ideas gel very well with radio astronomy. And that's all. I'll end with a sunset shot of the Karoo. If you're ever in Cape Town, come and visit us. We can fly up to the Karoo and have a look at radio telescopes and where it's going. Thank you.
Any questions? Go back to the GitHub.
Sure.
So do you, what kind of applications would you see for this speed for people besides you? I mean, can you describe something that you thought about?
So the question relates to the SPEAD protocol and could it be used elsewhere? I think one of the things that's of interest with SPEAD is it's a really low overhead way of exchanging and moving NumPy arrays around. So we talk a lot about distributed NumPy, and there's a lot of projects underway in that. And we haven't really thought too much about it, but I think it has applications in that kind of role where we say, how can you kind of very transparently and seamlessly move NumPy data around at very low overhead? And because this protocol works on FPGAs, for example, it's engineered to have a very low overhead, a very low footprint. It's UDP, and we easily get the full 10 gigabit E throughput with our Python stack. You can go straight into GPUs if you want as well. So I think we haven't really had enough time to spend thinking about it, but my hope is that there's use out there for the kind of distributed stuff.
What's the endpoint of the SKA sort of provided software? What does the pipeline spit out? Is it just the real space images, clean things, or is it just decorrelation?
Sure. So the question was, where does the SKA boundary stop? Where do we stop in terms of what we deliver? It differs a little bit, but essentially the mandate is to produce calibrated on-sky images. So as you mentioned, just image cubes, so frequency in one axis and sky coordinates in the other axis. For the SKA, though, even that gets to the point of being multi-petabytes, hundreds of petabytes big. So probably what we'll see for most kind of survey science is catalogs. So we'll produce a catalog list of that, and that'll be provided to the observer. But certainly we'll have to provide a lot of on-site data mining capability for people to send their queries to us. We've got to bring all the queries to data. We're not moving this stuff out of the desert just because of power concerns, if nothing else.
So one advantage of C of Fortran is that code that you write today, you are sure that it's still running in 20 years because it's standardized language. So I have made the experience with our institute. They developed huge amounts of code for Alba with Python 2.2. And at some point in Python 2.5, they had to rewrite large parts of their code base because Python is still evolving. It's not a standardized language. So do you see problems here? Did you hit this problem so far? It's a very long-term project for you, 2025. How we are 2013?
Thanks. That's an excellent question about if we write too much of our code in Python and it's changing and evolving from under us, how do we make sure that this code is not obsolete in 10 years' time and we can't use it? And I think there's two ways to address this kind of question. As you say, the one is to pick a nice, stable language that we know is going to stay like C, which we can use for the next 20 years. The other option is to hitch your bandwagon to Python with the risk attached to that. But basically what you do is you defer development costs. So my argument is if you can spend half the time now writing that code base, as long as you can account for the fact that you need to defer some developer time to maintain that code and update it as you go, or potentially throw it away as long as you keep the ideas, I think that helps you. And I think what helps as well with that philosophy are tools like good unit test coverage, good testing frameworks where you can afford to change code quite easily because you know you can just push a button, you can have a full test run on it, and you can be confident that your changes have easily been verified and are in place. But it's a very good point, something we grapple with, for sure.